Judi Sandrock from MaxIQ Space, and I'd like to take you through the slides for our ISS Rideshare 2025 workshop number 6, payload confirmations. The agenda for this session is why the deadlines are what they are, the ISS core versus the NASA HAB core, ISS payload options, the timelines and next steps, and then we're going to have another session after this where we're just going to go through the high altitude balloon payload options. The first thing is this is a screenshot from the Voyager NanoLab manual, and we can see here that we have some deadlines. The nominal deadline for hardware testing completed, that's MaxIQ Space's hardware testing has to be completed during May 2025, and the late deadline is June 2025. And then when we have a look at when the payloads need to be handed over to the launch provider, if it's SpaceX, it needs to be week 30, which is July 25th. If it is the Cygnus, which is launched from Wallops Island in Virginia, it's July 7th, which is week 30. Let's have a look at our deadlines in terms of our shared sheet. And in the description below, what I'm going to do is I'm going to put a link to how you can get access to that spreadsheet if you don't have access to it already. So the prototype custom payloads, we need the full description of this by March 31st, 2025. If you're only going to be using the white vanilla X chips, then we need to know by April 7th, 2025. Because what we need to do from MaxIQ Space's perspective, from our side, we need to submit all of our paperwork by April 8th to Voyager and NASA. And that is why when I go through the details of what we need from you by these deadlines, is that we need the data sheets of all the sensors that you're going to be putting on any kind of prototype board. You need to build and test your payloads. You have until May 6th to do so. The payloads are then shipped to MaxIQ Space. They need to leave you on the 7th of May so that they can arrive latest May 14th. And then we do our own testing and integration. It's very, very tight for us because we have to have everything done by end of May 2025. So please, we can't have your payloads late because we really do have to test everything. And please note, I've said here, no fixes. If your payload isn't working, if it isn't writing the data to the SD card, if it isn't behaving consistently, we cannot fix that. By then it's too late. So unfortunately, if your payload isn't working, we're going to have to leave it off. So what is the difference between these two cores? They can look very similar, and you can really only tell the difference when you have them next to each other. But the key thing is, and what we really need for this particular project is this ISS core. You can see here that it is slightly shorter. So when I put it up against this ruler, that's 80 millimeters, whereas the NASA high altitude balloon core is around about 85, 86 millimeters in length. The SD card interface is different. What it is it's where you slot it in, and this side of the core actually goes straight up against the wall of the NanoLab. So the SD card cannot actually get out by itself. We have to take everything apart in order to get the SD cards out. So that's another safety feature that we've built in. Whereas with the NASA high altitude balloon core, you've got this little flap that you then need to lock into place. And another big difference is that there's a camera connector here on the NASA high altitude balloon core. These ESP32s are different. On this NASA HAB extended core, it is the standard original ESP32, whereas the core on this newer ISS chip is the ESP32S3. For the ISS payloads, we can accommodate 4 of the standard size X chips. So what you could do is you could either use 4 vanilla ones, or otherwise you could use this IPB prototype board that has the standard connector ports. Alternatively, you could use the larger prototype board, the IPP NanoLab board. Please note that where these thick white lines are, this surface area is required to actually slot into kind of like a shelving system that we have inside the NanoLab. So no wires or solder or anything beyond that point. And that is why it's saying, please keep out of those zones. It's a little bit like an emergency lane. Please don't drive in the emergency lane. What you could do is you could use the 10-pin connector to connect the EPB. However, what's really important is that you have to keep within the 8mm height constraint. So that is 8mm from the top of your board to the bottom of the board above you. 8mm. You need to stick within that volume. So this is a screenshot of the shared sheet that we have. And you can see here that what we are looking at in terms of these deadlines is March 31st, 2025. We need you to submit, please, to Bianca Gottfredson, the components that you're going to be placing on your prototype boards if you are going to be having a custom payload. And that's the data sheets that you're going to be of the components you're going to be using, proof that the solution has been prototyped and tested, as well as proof that the payload uses the MaxIQ ISS core that is provided for operations and power, and that the data is saved to the SD card, and also that you are sticking within the mass and physical dimensions that you have for your rideshare slice. If you're using the normal white ice cream vanilla X chips, then we need to know by April the 7th which ones you're going to be using. So which 4 X chips will you be using? Proof that the solution has been assembled and tested by you, as well as proof that the data is being saved to the SD card using that ISS core. We need all of that. We just want evidence that you know that you've tested it and you are saying that it's going to work or that it is working. Because what we need to do is that we need to compile everything into our paperwork that we submit to NASA. So therefore, you cannot change your design after that. You can't come after the fact and say, oh, we're sorry, we actually think we're going to use another sensor, etc., because by then we've put all of the paperwork in. So if something's not working for you, unfortunately, you'll need to revert to some of our vanilla chips that we already have approval on. So what we'll do is, here we go. Our next workshop is going to be April 8th, repeated again on April 9th, and then we have our deadlines. So that is it from an ISS project perspective. After this segment comes the 2 workshops, the first version and then the repeat of workshop 6. So that's cheers for now. Welcome everybody to workshop 6 of our ISS Rideshare 2025. And in this workshop, we're going to go through payload confirmations, the timing, deadlines, all of that kind of thing. By the way, if there's anything that you want to add to the agenda or something, please put it in the chat, and then we can make sure that we cover it completely. My challenge is that when I'm sharing my screen, it's difficult for me to see the chat. So, Bianca, I'm also relying on you quite heavily here, maybe to abruptly interrupt me. So the agenda for today is we're going to have a look at the ISS core versus the high altitude balloon core because they are different. We're going to be having a look at that. Now that's interesting. You see what I did is that I moved things around, so it's messed up with the animation. We're going to have a look at why the deadlines are what they are, our ISS payload options, the ISS timelines and the next steps. And then after that, if anybody wants to discuss the high altitude balloon project, we can do that. I didn't want to mix it up too much with why we get together in this session, and that is all about our International Space Station project. So why the deadlines are what they are, and thank you very much to Mike Galvin for sending me an email about 2 weeks ago, literally highlighting a lot that was in the NanoLab payload manual that hadn't been included by Voyager in the contract. So it was quite interesting because I'd been I'd been working on the contract and I'd been looking at the contract, but then there was another document on their website that Mike was working with, and he was like, whoa, these things are starting to slip. So that is why everybody got this shock of suddenly there were these deadlines. So if we have a look at this, I've taken this literally copy and paste from that document, from the Voyager document. And if we have a look here, what they want is that they want us, MaxIQ Space, to have completed the hardware testing, launch minus 5 months. So if our launch is in October, early October 2025, that is the equivalent to week 40. So if we subtract 5 months, here we're looking at nominal would be May, and then late would be June. And then if we have a look here at when they need to turn it over to NASA for SpaceX, so that would be from Alex's window in Florida at Kennedy Space Center, Cape Canaveral, then that would be L minus 9.5 weeks. Interesting, 9.5 and not 10, but I've based our calculations on 10. That makes it July 25th. And then if it were the Cygnus, which is launched from Wallops Island in Virginia, close to Mike Galvin, relatively close to Mike Galvin, then that would be week 30, which is July 7th. That would have been my father's 75th birthday, but let's not worry about that. So really what we're looking at is we're looking at these dates of May, and we don't want to be late and having it go into June. So let's take that and then extrapolate that. So I've moved those deadlines to the bottom of the slide, and now I've had a look at our shared sheets, our shared Google sheet and our own schedule. And so what that does is that says for us to be able to do the testing of the payloads and integrating it into our structure that goes into the nanolab, we have to have that done by very latest end of May so that we don't go into June. Okay, so we need to have it with them by end of May, which means the very latest we need to receive everything is 14th of May. And I know, Bianca, I'm very pleased you're on mute because I'm sure that you are swearing, and there's certain swear words that whether they're in English or Danish, they still sound the same. So, so what we've got here is we've got for the teams to build and test your own payloads up until the May 6th, so that you can ship at latest May 7th. So what we need to do is by April 8th, we need to submit all of our paperwork to Voyager and NASA. So we have to include there every single sensor with the spec sheets. What are they called? Those information sheets that you get with to NASA. We need to have everything that. Thank you, Mark. Data sheets. Everything that our payload is going to contain within that nanolab, we need to have in our paperwork. So that is why we are giving until April the 7th for everybody to select if they have strictly vanilla X chips, which ones they're going to fly. And that is also why we have said by March 31st, please, you have to have sent us the data sheets for all of those components that you're going to put onto any kind of prototype board for custom payloads. So that is where these deadlines come from. So with your custom payloads, with your prototype payloads, you need to have made your decision before the 31st of March, so you can send us all the information by the 31st of March. And then you have up until the 6th of May to build it and test it thoroughly. And I really want to stress this because you can see here, this line here, no fixes. If your payload isn't working, if it's pulling too much power, whatever, we are just simply not going to include it in the NanoLab. We cannot fix anything for anybody. And I really, really have to stress that. You have to make sure yourselves that it's working, because if it's not working, then it doesn't go to the ISS. Because we cannot risk that we have something that is going to fail. So those tests, and really, Mike Galvin, Mike Wallach, please, we really need really need your input and advice and everything here for everybody on maybe what tests they should conduct, for how long, all of that kind of thing. So I think at this point, I'm going to stop sharing and I'm going to open it up to everybody to have their say.
Yeah, I will say that I'm a little relieved actually. When we saw the March 31st, we thought we had to ship our board to you by the 31st. So we have been scrambling for the last couple of weeks. We actually have our board built, programmed, and running right now. It's going to run for the next week to make sure that it works okay. So we can get the documentation to you. That won't be a problem at all. That does at
Great.
least give us a little bit more time for testing, which is good. But yeah, well, that's not an issue at all.
Great. Absolutely. Alex.
I'm still going with that green chip is in the corner. That's Richard. The rest are
Yes.
all standard chips. I just got the picture now, Richard, so I'll send it over. But of course, maybe I'll just turn off my background since I can't get the chips going. We're um we're standard except for the accelerometer piece that Richard's team is designing. So we'll be and we have the backup accelerometer as we go. So we should be good. That's what with the core. I just have my cores are all being tested with other stuff, but that's the that's my backup stuff. So
Fantastic. Bianca, sorry, you're still muted.
I built this the same version you had there for Richard. He sent me the details. So here it is with the ISS core attached.
Yep. There we go.
Great.
Yep. Identical. So that's what we're planning for.
Richard.
Yes, just quickly. Hi everyone. Yeah, thanks so much, Bianca, for just helping us there. We popped in the wrong core there, and obviously for correcting us on that picture. So we obviously what's really important to us is that everybody on our team has a copy of that slice. I would really love to get some input from the super boffins, Bianca and Mike Wallach. Sorry, is it Wallash? Wallach? Sorry, excuse the pronunciation.
Wallach, it's okay.
Okay. Just on testing, we have already put two of the sensors that we are going to put onto that prototype board. They're running separately currently. So we have the one accelerometer on the one, and I think there's another IMU I think on one of the others. They haven't put them together yet, but I am going to send pictures through to Bianca and to Alex just to see what they think. And Mike, your input on testing what we need to do would be super important to us because we don't know too much about that, and we definitely don't want to cause any trouble with a custom chip.
Yeah, I'd say the one thing that we're trying to be really careful of and making sure we check with our code is if you use a lot of code libraries for those sensors, a lot of them will have a while statement in there waiting for the chip to initialize. And those kinds of things can cause your program to hang up if one of your sensors were to fail. So you want to make sure that if you have a sensor fail, it's not going to stop the rest of your sensors from recording. So that's kind of the biggest thing. So like right now, so we're running ours for we would like to run it for a couple of weeks. Also, as you're logging your data, um, Excel has the limit of how many lines of data will fit in a spreadsheet. It's in the millions, I think, but I don't know if it's 1 million or 9 million. But as we were doing the math, we realized we were going to fill the spreadsheet in the 4 weeks or 6 weeks that we're on station. So we're actually breaking our file up. Once I forget how many lines of Excel sheet we stop and start a new one, just so that we don't fill it and then lose several weeks of data. So those are the two things that we've come up with so far.
Yeah, I think high level, like traditionally for space flight experiment, you want to do day in the life testing, and for a multi-week mission, um, it's great to do like weeks in a life testing, like Mike's saying he's doing. Um, what we key on is can our experiment and code survive unexpected power cycling? So if the whole nano lab for some reason accidentally gets powered down and powered back up, um, will our code restart and pick up where it left off on the SD card? Um, More in terms of environmental stuff, at the school level and the individual slice level, it's really debatable that you're not on the hook for doing any sort of environmental testing like vibration testing or thermal qualification, thermal cycling of your individual experiment. Um, One would argue that that's more appropriate at the stack level or the full nano lab level. But since we're using Voyager's own pre-qualified nano lab box, um, and the vibration environment on these particular launches is quite mild because we're usually going in the cargo bay of one of the ISS resupply missions. It's probably debatable whether even at the full stack level, um, vibration testing and thermal vacuum testing is merited. Also because the thermal environment is super mild for nanolabs. But yeah, at the slice level, at the experiment level, we are definitely going to do day in the life testing, and if we finish in time, we'll try to follow Mike's lead and do weeks in a life testing and make sure we survive power cycling.
Sorry, can I just confirm with your accent, you're saying a day in the life testing and a week in the life testing. So that obviously means running the entire cycle for a day, just to make sure that everything is working, and then a week in the life running the whole experiment for a week. So that is that what I'm hearing correctly?
Yes.
Okay, thanks. Thank you.
Yeah, if I can come in here, I am first of all, we've flown our X chips in a much harsher condition that we're gonna fly here with ISS. That they have actually not exactly these chips, but we never had a problem with manufacturing our chips and then not withstand a vibration testing or anything like that, even for going into space. But we have flown with the exact same setup with the same connectors, which could be the weak point here, and there has been no problem with that. So on the slice level, yeah, the most important thing on the slice level is testing that your code works. So the physical testing is not important. It's being put into a container. The container is transported under a fair condition, so not like anything super cold or super hot or anything like that. And in any case, all the components are able to deal with super hot or super cold while they're not running. And so if for any reason it's when they get it transported to ISS, that place is getting very cold, that's gonna affect anything. And I think there's a lot of other experiments flying that's much more critical temperature-wise than ours are. So I'm not nervous about any of that. Of course, it have to be assembled properly. And what's happening is they're being stacked with 8mm standoffs. There's going to be 8mm standoff between each board, and the whole thing is held in place and actually screwed to the bottom plate. So it's solid put together. And of course, it's inside the container, which where the whole setup is aligned to within, I think, half a millimeter or something like that. So there's no wiggle room to make anything loose or anything like that. So the most important, and both Mike and Mark have mentioned that, is power cycling. Make sure that your project works and the SD cards record data and all that kind of stuff if there's power cycling. The best thing to do is actually just do another SD card, another file on the SD card. So, don't keep writing on the old one. Just have a thing where you cycle through and see if SD cards, let's say you call them data 001. So you cycle through the numbers and figure out which one is available, and you take the next one, open that, and start writing to that. The size of the file, there is a limitation, which you just have to be aware of because of the SD card technology. So I'm not sure how much that's important here, because I never had a file that big. But if you put a 32 gigabyte SD card in, which is the biggest you can put in, each file should not be bigger than 4 gigabytes, which is still quite a big file. But I think there is on the partition system that we use on the SD card, there is a limitation to 4 gigabytes. So if you get over 4 gigabyte or 3.9, whatever, then start writing to a new file. The thing is that whatever data you have, if you have too many lines for whatever spreadsheet you have, it's fairly easy to make a Python program that split it into the right numbers, or take every tens or whatever it is. You can get ChatGPT to write the program for you. So it's fairly simple to do that. And if you want to have it loaded into Kibana, as Judi mentioned, when you have the data, you can run your analysis using that, and send the file to me if you upload it there. If you have really big files and you want to play around with data, there is a programming language that's called R. It's a statistic programming language that's meant to handle huge amount of data. Obviously, that could be another learning curve, but I just want to put it out there if you want to do that. And we did that last time we had a project on ISS. We got data down after a month, and yes, it was something over 1 million records or something like that. It was like a huge amount of records. And we used R to kind of like analyze the data. It goes pretty quickly with that. Or, there is a number of packages in Python you can use that pretty quickly can analyze data also. So the size you have to kind of like just consider is the 4 gigabyte. And one of the reasons why I think both Mark and Mike talks about running this thing here for a while is to try to get up to some data sizes where there might be a problem. So you might want to try to find that out, but preempted by not writing anything bigger than 4 gigabyte. And then, of course, there's other issues. Something can get too hot or too cold. Well, probably too hot, because in an environment where other stuff gets too hot. So one of the things you want to do is just maybe just at least figure out how hot your stuff gets when you run for a while. It doesn't have to run for a week before you figure that out, but just put your finger on the CPU or whatever, and just make sure that it seems like it's not getting too hot for you to run. The power source, when you're testing it yourself, you're testing with the PPU, the USB A pluggable power you can put into to the side of your project. So if I have my project here and I have to get power to that, I can of course use the USB port here, but I can also test it by, if you have one of these, these PPUs here, you can plug that into the side somewhere and then plug it into as a power here. Then that provides power because it's not going to be power on the USB here. So that's also an option. And then it doesn't matter how hot that gets because that's actually not flying. That's just for you to provide power for the board. Board gets power using these ends here. 4 different ways. So that's how it's powered, not via the USB, which you maybe do when you test it. So yeah, that's it on the testing side. But very important, make sure that you write to the SD card and your power cycle and you get the expected result when you just plug the power in and out.
Richard.
Great, thank you. So I just wanted to ask a silly question. Our experiment is based obviously on vibration testing. And Mike and was it Michael also mentioned something about vibration. Sorry, I missed what they were saying. So are you saying that the container that the slice is in is vibration resistant?
So what I was saying is on a traditional scale, the ride that we are going on to the ISS is quite a mild one historically. The cargo bay of the ISS resupply missions, I believe has padding or bubble wrap in it. So we suffer a milder launch vibration environment than a lot of other payloads or missions or experiments. So it's not nothing, but it's supposedly quite mild
It's
as
Richard,
defined on the
it's the
nano lab.
difference between getting there and being in orbit.
And being in. Got it. Got it. Yeah.
Will be good.
I was just hoping that was a little bit worried that maybe once the experiment is set up that it would also be in a vibration resistant container. But that's fantastic.
Yeah.
I panicked there for a moment. Thank you.
Absolutely. Bjarke Met she's put a comment in the chat about needing the data sheet for her 0G flight. So I'm just wondering, we have got a little bit of time with Met after this session, but Bjarke, maybe if you just want to share with everybody that the code that you changed to be able to accept the Bluetooth input, does that still write that data to the SD card? I'm just wondering.
Yeah, it does. So for you guys that maybe have missed it, I updated the software, the starter kit. So what it does is that as it boots up, it looks for a heart rate monitor, Bluetooth heart rate monitor, like the one I'm holding up here, which is one of these chest-borne heart rate monitors, Bluetooth, and the way they work is they turn on when they start communicating with Bluetooth. Yeah. And so what happens is that if it finds it, then it connects to it and it reads the heart rate and it writes that to the SD card. It actually also writes it out to the OLED display if you have the OLED display connected. I made that addition to the starter software. First of all, it's only in the startup. If you don't have the heart rate monitor, it's not going to look for it later on. So it have to be available from the beginning. If it's available from the beginning and you lose connection, we'll try to connect to it again. So it's not like it has to be perfect there all the time, but it will read the heart rate. And then for the COG mission that Amit goes on to here, we thought it could be interesting to measure the heart rate as soon as Amit experience COG. We expect that Amit is sending a signal out about that now we hit COG. And then we want to compare that with our COG sensor, or let's call it the accelerometer. So we can kind of figure out on the accelerometer when what happens. So the whole idea for us was, we also kind of pick up, proper pressure, a couple of other things about whatever sensor that we put together. But since it can take any of the sensors, and then it will just write out to the SD cards the various details. So yes, Amit, it depends on what sensors you gonna fly with. I can't remember. I suggested at least the accelerometer, but I think I also suggested probably the some of the other sensors.
So, one of the things about me is that I am a complicated human being. So here is the most recently update. Yes, on my chest, I'm gonna have a set of X chips. So it's gonna be CO2, temperature sensor, the pulse sensors, and I don't remember what is the other that my kiddos put. I'm gonna try to have the camera too, because my other students for the practicum, they are collaborating in a robot with Cornell University. So I am flying also a robot on that COG plane. I just sent a set of X chips to Cornell University for integration, because we're going to put a set of sensors, accelerometer, altitude. I don't remember right now what is the other, but I sent a set of X shapes and they're going to be integrated that to the robot. So there are going to be two different sets of X shapes flying in that COG plane. One inside the robot to track the movement of the robots, one robot, and then the others that are going to be on me. So it's going to be quite an interesting thing on that plane. And then the other thing that I don't want to mention it yet, but yeah, we can discuss that in the other meeting. So basically our different things going on. So for the ISS ride, we're gonna go with the standards X ships, because we're doing a lot of other stuff at the same time. And yeah, I don't want to complicate it, and I want to be, in compliance with the deadlines, because the deadlines for that are very similar for the other deadline that we're gonna discuss in the next meeting.
Great.
That's excellent. I have a number of different applications where I could track my heart rate. I don't have to go on a COG flight too. I want to check my heart rate in certain circumstances. Yeah, great. So if it's okay, what I'd like to do is, if I may just share again, and here we go. Great. So yeah, that's where all of these deadlines came from. So let's have a look at the difference between these cores, because you've received so many different X chips. So what I thought I would do today is take some photographs actually to show you the difference between these two cores. So for this project, the subject of this workshop is the ISS core. So that is, you can see it's slightly shorter than our normal standard extended core. And what I did is that I put it up here. We're looking at 79.5, or let's say 80 millimeters. This is a very standard stationary store ruler that I have here. So I'm not expecting it to be ultra accurate, but it's really, I mean, it's, roughly 80 millimeters, and the extender core is roughly 85 millimeters. So this one's slightly longer. And the reason why this core needs to be this dimension is because we've got these very strict confines with the nanolab that we have to fit within. Another difference is that with the ISS core, we don't have the camera port, and we have a slightly different SD card holder. The nice thing about the SD card holder is that this edge over here, this flat edge, is going to be right up against the spine. That's going to be inside the solid board, that's going to PCB, that's going to be inside the nanolab. So the SD card actually cannot come out when it's integrated into the nanolab. So it's only when you separate everything out that you're going to be able to remove that SD card. Whereas in this case, sometimes you may actually want to put some tape over it because you don't want it to dislodge with this setup here with the little slide, etc. So this is the difference between those cores. And so for the ISS options, and I put this together. So Richard, Alex, I didn't see any photographs from you, so I'm not trying to imitate what you've done here. But what you can see is that we've got 4 standard X chips, and we've got this IPB prototype board over here as an option. Then everybody received these IPP NanoLab boards, which are smaller than the board we would use for the HAB, the high altitude balloon project. And then you also have the 10-pin connector, which could take the EPB. But it's really very, very, very important that you keep within those constraints. Bianca, am I giving everybody too much volume by saying 10 millimeter?
Yes, so you are. Just share that screen again. So I just want to elaborate on a few things here that's is very important.
Okay.
So it's very important to understand that prototype board in the middle, the IPP, is not a board you can fly on the high altitude balloon flights. As you can see in the bottom, it only have 2 connectors. And the core that you're using on a high altitude have 3 connectors in the bottom, so you can't actually connect it. So whatever you develop and put on this IPP NanoLab board is not able to fly on a NASA HAB. And that's one of the reasons why I suggest that if you like, let's say you have 4 sensors, rather use the IPB that's on the left, the little green X chip on the left. Rather use that because you can use that both on the ISS and on the NASA HAB mission. So that's kind of important here. The other thing is that we have a standard height restriction in between the PCBs. So from your slice to the next slice, you have 8 millimeter. So and the reason why I say 8 millimeter is because the standoffs. So in those holes that are on the PCB, you will have a little metal kind of like a bolt that's 8 millimeter tall, and then we will stack the different layers together like that, and that means they're all screwed together. And the holes I mentioned before is the holes that you see in the middle board. So you can see there's 6 holes in the middle board, 2 on the top edge, 2 kind of like at the edge in the middle. No, in the middle board, Judi. There's 2 there, and then there's 2 there, 1 there and 1 there, and then there's 2 in the bottom of that board, and then there's a 2 in the bottom of the core. So those 8 holes are the 8 holes that been screwed together and stacked all the way up. And they should match, the whether you have an IPP nanolab or you have 4 standard X chips. We can stack them all the way up. So that's how it's being kind of like locked together. In the bottom, that the container that this is in, and Judi, if you stop sharing, I'm going to show on a container how it looks like. So this is the nanolab container that's inside. This is 100 millimeter by 100 millimeter. So from nanolab's point of view, they say this is kind of like the 1U size, but each wall is 3 millimeter. So that means we only have 96 in between. So this board here have to then go into a side panel here, like we call it a spine. So it goes into a spine here on the one side. Okay, and I have another spine here I'm using for something else, but so we have these 2 here. So you can see the board sits in between, and there will then be a stack of board here all the way down, and this will be 169 millimeter long. That's the amount of space we have inside, because there's also end pieces on this container here, and they take up some amount of space also. So we have a control board. So the board that I'm putting in that kind of like supply power and control it. And we have 1 in each end. And then in between, we have 15 payload slots. So there's 17 of these connectors in total. And if I put it in here in the container, you can see that it just fits in the height here in the container here. That's maybe difficult to see on the screen here, but it just fits into the height. This board here I have is too wide. It's something I use for the high altitude balloon, so I can't get that in. So it will fit in, and it'll be like a slack of like 1-2 millimeter to the different sides. Now the SD cards that I have here that sits there, it sits up against the wall of this container here. So once this container is lowered over it, that SD card cannot slip out. So it sits against the wall of the container here. That also means when we build it, the way the whole thing is built is that it's built with a plate in the bottom that's been screwed into so there's a station here at the bottom here, a plate here on the bottom that's been soldered on here, and then being screwed on. There's like 4 screw holes here in the corner, and that being screwed on here, and then the side panel comes on. The first side panel, we lie it down. We then slot in all the other project. We put the other panel on, and then we slide the whole thing down. And before we slide down, we can actually see if the SD cards in all the slots, and we can make sure that everything looks fine and gets slotted in. And then, and that's how we transport it. The control board I made here, this thing here gets USB connection, so the USB connection, and there's 12 volts that comes in here, and that gets distributed up against the side spine, all 12 volts, and that can then distribute it with power both from both sides into your board. So there's like redundant power supply to your board from both sides. And when we test it before, when we get everything together, we have a simulator that can simulate the USB here, so we can plug it in and simulate the communication and all that, and see that everything is working fine. So we will simulate it from that point, and then it'll be sent over. I can also just say that from the control board's point of view, it has a real-time clock on it. So I will be recording the real-time clock on the whole mission. So when we discover power surge and all that kind of stuff, we will be able to log when it happens, when it turns on and off, and all that kind of stuff. And that data will be available for everyone, so they can either match it to their. And the best way of doing it is that we will record the elapsed time, millis. That gives us the elapsed time. And I suggest strongly that's what you do too. So when you power up, you have the millis, and you can then compare with the data that you get from us. So that's and we've flown with the same real-time clock before. So, and we also had a power failure on ISS before, and we could then use that because that clock just continues because that's battery operated, independently of any other power. And that battery will last for a year or something like that. So we're pretty all right making sure that we have the exact clock. So that's a little bit about how it's coming together from our side. Back to you, Judi.
Jaco, thank you. Thank you very much. And so what I did is, while Bianca was sharing that with us, what I did is that I changed that to 8. Mike Galvin, please.
Bjarke, can you remind us, have you yet posted the code snippet for live data downlink?
I haven't.
Because
we're talking
about the urgency of doing day in the life testing, and I'm not sure
Yeah.
we even have the code we need yet.
No, that's correct. I haven't actually done that piece of code. In reality, it's very limited what we can have of data. So I have it as a high priority to make that code snippet. But it's just a call to make sure that everybody knows that their project is running. We'll probably be able to have it running like more than once, but the way but I will put the code together, and I will explain in the code how it is. But it's going to be like a one-line code to kind of like do this communication, so it doesn't interfere too much with the code you have already. But yes, there is going to be and I agree with you. If you want to run week-long exercises, then you should have that code with you. But I'm working hard on getting that. But you don't have it yet, so I can confirm that.
Okay, thank you.
So for the 8mm, we're talking from the top of the board to the bottom of the next board?
That's correct.
Okay, so for reference, as I'm looking at this, the actual processor chip is already 5mm off the top of the board, so you really can only go a little bit above that chip.
Yeah. So that's not a chip.
For reference
That's a
for
connector.
everybody as we're going.
Yeah.
So if I took as backup, Richard, I ordered a 9 degree of freedom accelerometer from Adafruit. And I can get it on, trying to get it so that it fits well inside the parameters. So that's a full on board, even with the connectors, which I would probably break off.
Yeah.
So you get an idea. Yeah.
I'll pop the pictures of their board prototypes into the group a little bit later. I'm just waiting for them.
Yeah.
They're very rough. They also want to encapsulate the entire board, well, the entire chip in a resin. So yeah, just to make sure that everything's insulated. So yeah.
So, Alex, that chip you have there,
Yes.
just consider that you can actually mount it with those connector down. So
Oh yeah, good point.
yeah, okay, you get what I mean. Because
Yeah.
then when you use when you have these kind of pins here, these kind of pins that you probably got with your board, they have like a little bit of standoff. Alex, these ones here.
Yeah. Yeah. No, I got.
Yeah, exactly. So if you put them in a board and you put the board, face down, which doesn't really matter, it's dark in there. If you put it face down, then the connectors are sharing the space as it is with the space that stays on your connectors there. So then it gets lower.
Yeah.
But yes, you have 8 millimeter from the top of your board to the bottom of the next layer.
Yeah, I'm just my big challenge at this point is just this is for fun from my side, trying to figure out how to rewire where the pinouts are properly.
Okay.
Because
I just want
again,
to.
it would be so nice if somebody's third party device matched up perfectly with the pinouts on the prototype board, but it doesn't. So
Which is one of the reasons why we did this system in the first place.
yeah, no, it makes I have my notes on how to jumper everything from the last presentation.
Okay, that's good. I just want to ask Mike and Mike, who also do prototype stuff. Do you have a problem with the 8 millimeter?
I think we're going to be, that's our concern is whether or not we're too thick. I think we're right at 8 millimeters. We were actually going to try to sand down some of the pins on the back of the board where they're soldered to the board to get them as flat as possible to get us as close to that space as possible. Then the other question I had for you is, in your pictures, when you're clipping everything into the spine, it looks like the proto board width is wider than your microcontroller board, right? Is that still going to fit okay in between those spines?
Yeah, no, now I don't have that board here anymore because I think Judi stole it from me. So she could show it to you in that presentation there, but it will fit. The thing is that if Judi, if you have a time, then please pass me the board. So here is the headphones. Thank you. Just allow me to put it together here. So you can see here that the reason why this board is shorter is because it have to go into this connector. And this board here is flush up against the spine here, okay? And the reason why we have this like white line is because that white line represents that we have these small chips here that's all like that height. And they don't sit on the board where this board meets, okay? But they sit right next to it, if that makes sense. So so if you can understand in here, sorry, I have to find the camera here. Here we have like some chips sitting here that provide power and the CAN bus connecting and different things for each board. And therefore I have this white line that tells that you can't go further than that, okay, on the board here. But otherwise it goes all the way down to the board, and we're also going to use that to hold on to the card here. So we both stack them, and we also have in the spine here we have a 3D printed frame. You can see it on this board here. There's this 3D printed frame here where when we slide it in, it's also been held in on that level there. So that's what kind of like this white line here represents. But as you can see, we have it's the perfect dimension here to fit into the spine here. And the black connector here is the reason why it looks shorter here.
Okay.
Bjarke, we're in the same position probably as Mike. We're flying 3 experiments, and one of our sub-team's experiments is like right at 7 millimeters tall already, and they're trying to decide on one tiny little thing to put on top of it. So we're line to line on one of our experiments is line to line on 8 millimeters. So but my ace in the hole was I was going to ask if Princeton could have the top slot in the stack, which I expect has a little slightly more room, but it sounds like I might have to flip a coin with Mike for that one.
So there's a couple of other options that I'm going to discuss with Judi. So that's the reason why I want to figure out if there's. I mean, Judi, I only know that Mike and Parklands are doing prototype boards. There's nobody else who's doing, huh?
There's a possibility that Jim Gorman's students
okay.
from NIPMAC would be doing something.
Okay.
Yeah, Bjarke, what we could consider is let's have a chat about it.
I'm holding my students strictly to 8 millimeters, so we'll deal with the fallout.
Please do that for now, Mike, if that's okay.
Yeah, but Mike and for that matter, Alex, if you start, getting the angle grinder out, then just give us a call before you power
do that
on.
Yeah.
Oh, I look at it as I got a whole bunch of these little prototype boards I can mess up before. And I'm doing it just for fun on my end. Richard's got all the stress for everything, so I'm good.
Yes. Richard's first in the line for the heart rate monitor.
Yeah.
So great. Okay. Bjarke, let's discuss this offline and then we can come back to everybody. Okay. Good. So let me share once again. Okay. There we go.
Can you scan back to the latest deadline so we can all take a screenshot of that or something?
This one.
Yeah.
Okay.
Thank you.
Fantastic. So here is a screenshot of the of our shared sheet. And what I'm going to do is that I'm going to put the link to this shared sheet into the chat when I stop sharing, just so that everybody knows that it's there. And so what I've done is that I've updated it. You can see this is today's date with this workshop now today, and then here's tomorrow's workshop, which has also been scheduled. And this is really basically what we're covering. And then the deadlines, March 31st for custom payloads, to let Bjarke know what components are to be placed on the prototype boards, proof that the solution has been prototyped and tested, and proof that the payload uses the MaxIQ ISS core provided. We just want to make sure of that. And then for operations and power, that's provided for operations and power, and the data is saved on the SD card, and then the mass and the physical dimension. So we've had a lot of discussion around that. And then for those standard vanilla white vanilla ice cream colored X chips, just to submit also to Bianca which X chips are going to be used, proof that the solution has been assembled and tested, and then proof that the data has been saved to the SD card. So that standard software for the starter kit, the STEM kit, we know if you go to in the in any of the getting started guides, if you need links or anything from me on as a reminder of where to go on GitHub, that coding example has been developed by Bianca so that it automatically saves the data on the SD card. So what you can do is also just try it straight off, because if I remember correctly, we loaded that code onto these ISS cores in order to test them. So please just have a look. It's quite possible that that code is already there on that board for those vanilla X chips. And then the rest of our deadlines, we're going to have another workshop April 8th and April 9th. And then our deadline to ship everything needs to be shipped at latest on the 7th. That's it in terms of the ISS project. So I was just wondering, if there's anything else to discuss in terms of our ISS project, or do any of you want us to go into what is going to happen with the high altitude balloon project?
I just had a question for you on the proof of testing. What kind of documentation are you looking for there? Like for us, like we're doing bench tests and longevity tests and stuff like that. Do you just want that as a written document kind of outlining what we've done, or
just, Mike, I don't know. It's actually for you. It's more for you than for us. I mean, for us, yeah, I mean, we would obviously we want to know that it's going to work, and it's not going to cause any problems. But yeah, whatever, a photograph, a screenshot, or whatever, You've got the data on the SD card, you've got a CSV file and a screenshot or something. And Bianca, help me out here, please.
Yeah, so Mike, the important thing for us is that we can't risk that people get surprised about deadlines or when things have to be ready or that kind of stuff. So this is actually just like a go no go decision point. If you come back to us and say it's working, we're not going to check whether it's working or not working, but you will have come back and say it's working. And therefore, you're not going to come back to us and months later say, I need more time, I can't get it to work. So if that makes sense. So if you say it's working on that day, then it works. But if it doesn't work that day, then we have to figure out whether where you are in the process. And that's important thing for us. We just need to make sure that this is not something that's is being thrown together in the last minute and maybe not work or whatever. In reality, the way that the setup is on this thing here is everybody gets provided their own power. There's a power chip for each. If they draw too much power, then it doesn't work. There's plenty of power, so don't worry about that. But we can't have that somebody do something on one slide that ruin for anybody on the other slide. So everybody have their own power thing, and that being provided with dual power supplies from both sides of the setup, and those are automatically just turning off if there's too much power being drawn. So the whole thing for us is that we want to just make sure that you say that your stuff is ready. So when you plug it in, you are happy with whatever result that comes back, and you have it, and it working. And it's as much so you can say to your students or to yourself or whoever is doing this thing here, listen, we have a deadline here. You have to make it ready, otherwise we can't fly. So that's the purpose of this deadline.
This is the repeat workshop of the one that we held yesterday. And we do have an agenda. And the first item is why the deadlines are what they are. Then we're going to have a look at the ISS core versus the NASA high altitude balloon core. I've had some feedback that maybe there's a little bit of confusion around those two different cores and the different applications. The ISS payload options, and we have a few slides from the students from Nipmuc Regional High School. They have actually built and tested their payload, so they got some photographs to show us, and then we'll discuss everybody else's payloads, the timelines and the next steps. And for those of you who are interested, at the end we can have a session where we have a look at the NASA high altitude balloon projects. Great. So let's have a look here at these deadlines and why they are what they are. So Mike Galvin drew my attention to the integration manual that was supplied by Voyager, who used to be NanoRacks, in terms of the NanoLab. This was actually a document that I hadn't received directly because it's a document that's on their website. I'd been so busy looking at the contract and when we have to pay the different tranches and those conditions and all of that kind of thing that I hadn't actually had a look at these timelines. And Mike Galvin drew my attention to this. And that is why you suddenly got this flurry of emails. So if we have a look here, our deadlines are based on an October launch. So L is October in week 40 of this year. So if we have a look, the hardware needs to be tested, completely tested by us on our side, L minus 5 months, which makes it the nominal, or they would say, I guess we would say in English, we would say preferred. In space lingo, they will say nominal is during May, and then the late date is June 2025. So this is also something that has changed in that what they've done is that they've put in these conditions here in terms of turning over the NanoLab to NASA, is that for SpaceX, it's L minus 9.5 weeks. Very interesting that it's 9.5 and not 10. But anyway, so that brings us to week 30 of this year, July 25th. Whereas if it's getting launched on the Cygnus from Wallops Island in Virginia, which we really doubt. However, if it is with the Cygnus, then it's going to be week 30. No, that can't be week 30. I did that incorrectly. It's July 7th. So that's actually, that's going to be week 27, week 28. I need to correct that. So what I'm going to do now is I'm going to I've kept the May and the June nominal and late dates respectively. And then by working backwards, that is why we come up with this date of March 31st, 2025, for us to understand the description, or us to have the description of your payload. So what that really means is that if you're going to be using the prototype boards, what we need from you is the data sheet for all of the components that you're going to be putting on those boards, because we have to compile our paperwork to go to NASA. When it's X chips only, if you're going to use the normal vanilla white X chips, we already have those in our paperwork. So then it's actually very easy. You just let us know which 4 X chips you're going to use, and then that's pretty easy for us, because we need to submit our paperwork to NASA and to Voyager on April 8th. So that is less than a month away. we need to submit the paperwork. So you don't need to have the payload itself absolutely ready. You just need to know which components you're going to use. And it would be really great if you have tested them already and you know that that's what you're going to use. Because unfortunately, after March 31st, we can't change anything. So if you found that maybe your component didn't work, your sensor didn't work that you're putting onto a prototype board, then you would need to revert to one of the standard X chips that we already have the paperwork submitted for. So in terms of building and testing your payloads, that will be up until May 6th. We need you to begin shipping your payloads, or actually ship your payloads latest May 7th, so that it definitely arrives with us in Cape Town, May 14th, 2025, because then we only have 2 weeks before we are going to ship it end of May. So here we're looking at just right in the middle there between green and red. What is that? Yellow or something like that. So we're looking at that. We're really pushing that. If we're able to get that, if we're able to get everything to them by the end of May. So at this point, what I want to do is that I want to stop sharing and I want to see if there's any comments from anybody, or anybody wants to discuss that at all.
Judi, one question from Nitma. We're using 2 SparkFun sensors, so we can just download the data sheet from SparkFun. Is that what that's what you're looking for?
Please.
Perfect.
Yes. Yeah, absolutely. Bianca?
Yeah, just whatever SparkFun sensor you're using, just supply us with a data sheet from them. And to make it easy for us, just give us a link to a SparkFun page where you found the things. Sometimes, and the reason I'm saying it, sometimes they come out with different versions. Some have quick connect, some doesn't have quick connect, and so on. So they sometimes have this exact same chipset on different boards. So just give a link and then a data sheet that's on the specification from SparkFun.
Gino, I think you were wanting to come in.
Can you hear me?
Yes, we can.
Awesome, thank you. So I had a couple questions. So we have our this is an earlier prototype of our board, but I wanted to know, so in the documentation for the height that we can get to, I saw is it 8 millimeters from the top of the board?
So it's 8 millimeter from the top of your PCB to the next PCB above you. Okay. So we use 8 millimeter standoffs between the boards. So okay. So that's the height that you have. So each layer is 9.6 millimeter, if you can imagine that, because that's 8 millimeter plus the 1.6 millimeter PCB.
Okay. And then on the bottoms, we have a couple through-hole components. Would you prefer us to cut down the tips of the pins on the bottoms, just so that, because there's probably about 1 millimeter of pins sticking.
So if you cut it down, obviously other have used a PCB similar to this thing here, where there's connectors and they stick out on the other side also. Okay. So if you can kind of like keep yourself lower than that, that will be ideal. Okay. Our PCBs, of course, surface mount, so there's nothing there, and some of them are, there's not a lot that's happening on the surface of it. So there's normally we can find space, by mingling them around. And also, if you have a problem with your 8 millimeter, then let us know, okay? But try to keep it in with 8 millimeter, and then let us know if for some reason that is a problem, because one of the things we can probably play with is like figure out how we stack it together and things like that. But we just need to know upfront that if you have a problem.
Yeah. And then I guess my last question is, so we have testing for all of our sensors. The at this point, our last sensor is our kind of custom gamma ray detection sensor, and we're kind of still in the process of figuring out testing because we had to get a whole bunch of stuff a bit last minute. But after next week is when we're going to kind of start our kind of final wave of testing. And at that point, the only thing that we would be swapping out would be the capacitors and the resistors, which have the same data sheet that we would be supplying. So like I have already compiled most of our resources, and all of the capacitors and resistors are within the same family. Would those be fine to swap out?
Yeah,
Like changing from like a 10 ohm to like a 12 ohm, but it's the same company and same data sheet.
So especially on the resistors, I'm not too nervous. If your capacitor changes like from 100 nano to 10 farad or something like that, then I start getting nervous.
Yeah.
So but if you, like, say for example, you use a 10 microfarad and you want to change it to a 22 microfarad, and they're the same tantalum or whatever caps, then it's all right. Then it's not a problem. The thing is that we will forward it to them and to Voyager as soon as we kind of like compile all this thing here, and they will go through and figure out if there's any problem. I don't expect any of this kind of stuff giving any problem. The thing is that if you use like any kind of like special sensor that maybe produce a lot of heat or have outgassing or that kind of stuff, that could be a problem. And the main thing, and again, I just want to reiterate what Judi said, is that we just want to make sure that you don't, after the end of the month here, say, we like to use something completely different. And what we kind of like hope for is that by end of this month here, you have your hardware kind of like locked down, and you can start running software tests, because the software is of course can change until you have to supply it.